So this is all funded by the Air Force, but they only pay for the construction. Batteries are not included. So in order to get PS1, originally a prototype to test the hardware to get science out of it, we had to go and raise about $3 million a year in operations funding, but we found some friends with deep pockets. That's where the telescope is. Here's the picture I showed you earlier. Here are the surveys that we're going to carry out. So the two interesting ones here are the big numbers, 56% of the time on a 3 pi survey, 30,000 square degrees, and 25% of the time on medium deep fields. So those will very rapidly and are already as deep as we will get in 3 years with 60 or so visits in the 3 pi survey. So we'll learn using the medium deep fields and then apply the refined procedures to the full survey. This is the good and bad chips in the detectors. This is showing the read noise, around 6 electrons for nearly all of the devices. So that's not quite as good as we wanted, but it's adequate. It's driven by other science goals to get very short exposures. The quantum efficiency is very uniform. Here's the full width half max statistics. We're basically getting 1.2. We believe that the side is delivering about 0.8, the natural seeing and so on. And we know that the optics is delivering 0.6, or failing to deliver, smearing at the 0.6 level. And the rest is thermal effects, dome seeing, and so on. And so this is the kind of image quality we get. These are, again, median star images across the whole field. And as you can see, it's very uniform. Sub-arc second seeing when the seeing permits, but more important for us, very low systematics. Here's some nice results where during the so-called demo month in April, we simulated what we would get in 3 years for the whole of the sky on some patches, the small area survey. And this shows what we've done is a comparison of what we get to what SDSS gets. So they're grainier because they have bigger pixels and so on. But in the G band, you don't see a great difference in terms of the number of objects detected, though we have better resolution. But as you go to the redder bands, here's the I band and the Z band, you can see we really detect a lot more objects there. And so, you know, it's not orders of magnitude more, but it's significantly more. It's going to be maybe half a magnitude deeper than the Sloan survey. It'll have image quality of about 1.2 arc seconds instead of 1.5. But perhaps the biggest thing, and this comes simply from the fact that we have 7 square degree field of view as opposed to 1.5 square degree, we'll have about 4 times the sky to play with. So instead of 7,000 square degrees, we'll have 30,000 square degrees. That's just a picture of some photometry. Here's a demonstration proof that we're detecting supernovae. Here's the first Hubble diagram from Pan-STARRS 1 based on 30 supernovae. There's the beautiful site and the young, excited operators. Here's some PR images of things that we've found on the sky. And so, you know, I've run out of time, so I won't read through this, but I think we're doing pretty well on the image quality. We paid a huge amount of attention to things like getting the focal plane flat, right? That's a real bugbear in things like CFHT. So if you compare, for instance, our image quality, that's just a contour plot of the same thing, with what we were getting from the 12K, where you can see, I hope, that it's supposed to show that there's quite large chip-to-chip variations of the PSF, discontinuities between chips and so on. Here's some statistics of our full width half max. We're actually averaging better than what we got in demo months, but never get better than about 0.7 arc seconds, unfortunately. This Q statistic is the quadrupole moment of the stars in pixels, so it's very, very small. That's good. Here's what we get in the G band in one lunation. R band, I band, Z band, and Y band. Right? So this is how much data there is. We're not talking about 100 square degrees here. We're talking about thousands of square degrees every month. And this is what we've got to so far, and the system basically hit the road running in the middle of December. So that's what we've done. This is where we're going with Pan-STARRS 4, and I see that my chair is standing up, but he's too polite to encroach on me, so I'll stop there and take questions. Thank you.
Thanks, Nick. Well, it's quite a large room, so if you're wanting to ask a question, if you could wait for Emma or Muten to come to you with a microphone. So, questions?
Well, that must have been clear.
So what are the chances of Pan-STARRS 4 happening?
Well, we're funded for Pan-STARRS 2. We hit a bump in the road because we were tied up in legal challenges. Someone sued our contractor last year. But the optics for Pan-STARRS 2 are generated and are being polished. So we're getting interferometry and stuff. So Pan-STARRS 2 will be on the sky in 18 months, if all goes well, and will be initially placed next to Pan-STARRS 1 in the old Magnum Dome. And we get funded year by year, but what I'm hoping is that, you know, PS1's a success, right? It's generating science data every night that the weather permits. And there's people like NASA who are being pushed very hard to fund the asteroid searches. And so we're hoping that the future will be good for getting future funding and maybe decoupling us from the Air Force funding.
Conrad.
So you made a great remark that the design of LSST is flawed and that this is the way to go. Can you say a little bit more about that?
Well, that's an interesting question, because so this is, you know, what people are predicted Pan-STARRS 4 would do. Here's LSST. Is this the right way to go forward? Obviously a very ambitious thing. And, you know, Tony was right. For years he'd been saying we need a powerful system dedicated for weak lensing. And that's what we followed in doing Pan-STARRS 4. But if this has got fewer pixels than Pan-STARRS 4, right? So is this the right way to go forward, right? It's required 2 decadal reviews, and it's going to require at least a decade before we see any data from it. I mean, personally, I'll be retired, you know, and many of the people involved will actually be dead, you know. So you know, how are we going to use 100 billion pixels? You know, this is the curve, right, which has LSST over here at 2014. Well, we know that's not going to happen. Right? Once you push that green point out to the right, it's well below the curve. So I don't know what is going to be on the curve, but distributed apertures could become very, very cheap. There's people making these 1 meter carbon fiber systems, and we have ways of controlling mirrors, analyzing the optics to control these things very powerfully. The other thing that I would be extremely afraid of if I was an LSST proponent is the Arctic sites, both you know, Dome C and Dome A, and the Canadians having Ellesmere Island, because a mere 3.5 meter telescope in one of those sites would be equivalent to an 8.4 meter in Chile. So that's my sort of crystal ball.